The classic Greek definition of tangent is based on SOHCAHTOA, which says that the tangent is the opposite side divided by the adjacent side. So if our angle is theta, our opposite side is A, our adjacent side is B, then the tangent of theta is given as A over B. And this works for triangles, but it doesn't yet work for our circular definition of radians and trigonometry. The circular definition of tangent is based on the unit circle, and let's say we have an angle theta in standard position here. Recall that we've defined the sine and cosine in standard position to be the sine of theta is the y-coordinate for a unit circle, and the cosine of theta is the x-coordinate if you have some point P on the terminal side of angle theta. Now, if we draw this triangle in the unit circle, we can draw the line down to make a right triangle. And the radius is 1, which is actually not important for tangent because tangent doesn't use the hypotenuse. What it does use is the opposite side, which is the equivalent of the y-coordinate, and the adjacent side, which is equivalent to the x-coordinate. So we can say that for an angle in standard position, the tangent is the y-coordinate divided by the x-coordinate. And it doesn't matter whether it's a unit circle or a larger circle because the radius is actually not involved. One point to note, this radius here makes a straight line. And if you look at the slope of this line, the slope is the rise over the run. So another way of thinking about the tangent is we sometimes say the tangent of theta is the slope of the line made by the terminal arm. Okay, so for quadrant 1, this is still consistent with our classical Greek definition, but we'll see in a second that we can also apply this to quadrant 2, 3, and quadrant 4 angles.